Our universe might be built on a lie. For over a century, physics has rested on two pillars. One, Einstein's general relativity paints space and time as a smooth, continuous fabric, a cosmic stage where the drama of planets and stars unfolds. The other pillar, quantum mechanics, whispers that at its heart, reality is grainy, uncertain, and strange. These two views are incompatible, and their clash points to a mystery at the core of everything. What if the stage itself is an illusion? This is the radical idea of emergent spacetime, the notion that space and time are not fundamental ingredients of reality, but are themselves born from something deeper and more basic. Much like the warmth you feel emerges from the frantic dance of invisible atoms. By the end of this exploration, you will understand the 25 specific cosmic clues that could prove our familiar reality is a magnificent mirage. We will see how black holes hoard secrets and why the vacuum of space might be hiding its true nature, all pointing to one staggering possibility. What does it mean for reality if even time is not what it seems? One of the most profound challenges to our classical view comes from the darkest objects in the cosmos. A black hole, according to Einstein's relativity, is a place where space and time become so warped that nothing, not even light, can escape its pull. If you were to fall in, you would cross a point of no return called the event horizon, and according to the old textbook rules, you and all the information that makes you would be crushed into an infinitely dense point, a singularity, and simply vanish from our universe. This creates a terrifying paradox for physics. Quantum mechanics has a sacred, unbreakable rule. Information is never truly destroyed. It can be scrambled, hidden, or transformed, but it must, in principle, always be recoverable. A black hole, by permanently swallowing information, seemed to be committing a fundamental crime against the laws of reality. For decades, this black hole information paradox stood as an impasse, a glaring sign that our understanding of spacetime was incomplete. The resolution, many physicists now believe, points directly to emergence. The key insight is that information is not lost inside the black hole. Instead, it is meticulously preserved, but in a way that shatters our classical intuition. The information of everything that falls in becomes encoded on the surface of the event horizon itself, like a cosmic hologram. Think of it like this. If you burn a book, the information seems lost in the smoke and ash. But if you had a perfect, unimaginably powerful microscope, you could, in theory, trace the movement of every single atom and reconstruct every word. The information was never gone, it was just transformed and spread out. For a black hole, the event horizon acts as that transformative surface. It scrambles and stores the information of the infalling matter in a quantum state on its two-dimensional boundary. This is the heart of the holographic principle, the idea that all the information needed to describe a three-dimensional volume of space, like the interior of a black hole, can be written on its two-dimensional surface. This is a direct clue that our three-dimensional reality, with its depth and flow of time, is not the fundamental layer. It emerges from a vast network of quantum information painted on a lower dimensional surface, a reality where the very concepts of inside and outside break down. The preservation of information forces spacetime to have a quantum, pixelated structure at its core, revealing the smooth cosmic stage as a beautiful, convincing illusion. This holographic principle is not just a clever trick for black holes, it is a potential law for the entire cosmos. Imagine your entire reality, every object in your room, the air you breathe, the very space that contains it all, being a projection. The information needed to create this three-dimensional world, in all its rich detail, could be entirely encoded on the two-dimensional walls surrounding you. It is as if the universe we experience is a magnificent, immersive movie, but the master film reel is a flat, quantum data sheet existing on the cosmic boundary. This profound reduction in dimensions is our second major clue. It suggests that spacetime itself, along with the force of gravity that bends it, is not a fundamental ingredient. Instead, they are collective phenomena that emerge from something far more basic, a vast network of quantum bits of information interacting on a lower dimensional surface. Gravity, in this view, is not a fundamental force like the others, but a thermodynamic effect, a kind of statistical glow arising from the underlying quantum chaos, much like the concept of temperature emerges from the random motion of molecules. This provides a direct mathematical framework for how emergence could work. The equations show that the smooth, continuous geometry of Einstein's relativity can be derived from the statistical behavior of countless quantum degrees of freedom living on a boundary. The three-dimensional world with its gravity and flowing time is not the primary reality. It is a calculated projection, a best-fit image generated by the system. So the solidity of the floor beneath your feet and the vast emptiness between stars may both be grand illusions, secondary effects of a deeper, information-based reality playing out on a cosmic screen we cannot yet see. If this is true, then what is the true nature of that hidden quantum data, and how does it stitch together the seamless reality we perceive? This leads us to a third and deeply strange clue found in the mathematics of nothingness itself. In the quantum vacuum, empty space is not truly empty. It is a seething, bubbling ocean of virtual particles flickering in and out of existence. Physicists studying this quantum foam discovered something counterintuitive. If you draw an imaginary box around a region of this space and ask how entangled the quantum information inside is with the information outside, the answer is not what you would expect. Classically, if something depends on volume, you would expect more stuff in a bigger box to mean more connections. But here, the measure of this quantum connection, called entanglement entropy, does not scale with the volume of the region you are looking at. It scales precisely with the area of its surface, the boundary of your imaginary box. This is a profound area law. It means the quantum complexity, the hidden links that stitch reality together, is not about how much space you fill, but about the surface that contains it. This is eerily familiar. It is the exact same behavior we see with black hole entropy, where the information content is proportional to the area of the event horizon, not the volume of the black hole's interior. This mathematical mirror is not a coincidence. It is a flashing sign that the same fundamental principle is at work in both the extreme gravity of a black hole and the quiet vacuum of empty space. The area law is a hallmark of emergence. It tells us that the geometry of space, the very distance between points, may be woven from a dense fabric of quantum entanglement. Think of it like the threads in a piece of cloth. The strength and texture of the fabric do not come from the threads themselves, but from how they are woven together, how they are entangled. In this view, space is the fabric, and every quantum connection is a single thread. The more entangled the underlying quantum bits are across a boundary, the more space and the smooth geometry we perceive emerges from that connection. So the three-dimensional world you see is not built from tiny blocks of space, but from an unimaginably complex web of relationships. This suggests that if you could somehow cut all the quantum entanglement along a surface, space itself would literally fall apart along that boundary. The distance between 2 points would become meaningless because the connections that create distance would be severed. This is a radical reimagining of reality, where the universe is not a container for things, but a network of relationships. And if space is built from entanglement, what does that imply about the nature of time? But if space is woven from entanglement, then the event horizon of a black hole presents a terrifying puzzle. This puzzle, known as the Firewall Paradox, is our fourth cosmic clue. It begins with a simple, unsettling question. What would you actually experience if you fell into a black hole? According to Albert Einstein's theory of general relativity, the answer is nothing special, at least not at first. If the black hole is large enough, crossing the event horizon would be uneventful. You would not see a wall or feel a sudden jolt. Space and time would smoothly warp around you, and you would continue inward, unaware of the point of no return you just passed. This is the principle of locality, the idea that physics happens smoothly from one point in space to the next. But quantum mechanics tells a very different story. Remember the holographic principle, where all the information about what fell into the black hole is encoded on the horizon. For this to be consistent, the quantum particles just outside the horizon must be intricately entangled with particles that fell inside long ago. This entanglement is the glue that holds the geometry of space together. Yet there is another quantum rule. A principle called monogamy of entanglement states that a quantum particle can be deeply entangled with only one partner at a time. The paradox arises when we consider a particle escaping the black hole as Hawking radiation. For information to be preserved, this escaping particle must be entangled with the radiation that left earlier. But for space to be smooth at the horizon, that same particle must also be entangled with its partner that fell inside. It cannot be both. To resolve this contradiction, one of these entanglements must be violently severed. The mathematics suggests that if the entanglement with the interior particle is broken to preserve the information in the Hawking radiation, the result at the horizon is not smooth space. Instead, it becomes a seething, energetic barrier, a literal wall of fire composed of ultra-high energy particles. An astronaut crossing the horizon would be incinerated in an instant, contradicting Einstein's prediction of a smooth passage. This is the firewall, a concept so jarring it forces physicists to choose. Either general relativity is wrong at the horizon, or our understanding of quantum information is flawed. Most attempts to resolve this paradox lead to the same profound conclusion. The very idea of locality, that you can smoothly move from one point in space to another, must break down. The firewall is a signal that spacetime itself, as a continuous local entity, is not fundamental. It is an approximation that fails under extreme quantum scrutiny. The event horizon is not just a place in space. It is a boundary where our classical picture of reality dissolves, revealing the pixelated, non-local quantum network from which it emerges. The firewall paradox is not necessarily a prediction of a real wall of fire, but a brilliant flare illuminating the fault line between two worlds. It tells us that to save quantum mechanics and preserve information, we must let go of the naive picture of spacetime as a smooth, continuous stage. The smoothness is the illusion, and the firewall is the stark light revealing the seams. The mathematics of black holes delivers a fifth clue so precise it feels like a direct message from the universe. In the 1970s, physicist Jacob Bekenstein made a startling proposal. A black hole, he argued, must have entropy. Entropy is a measure of disorder or hidden information in a system. Think of a tidy room versus a messy one. The messy room has higher entropy because there are countless ways the items could be arranged, hiding the original, ordered state. Bekenstein realized that when matter vanishes behind an event horizon, it takes all its information with it, creating a state of maximum hidden disorder. Therefore, a black hole should be the ultimate entropy container. Stephen Hawking initially resisted the idea but was later convinced, and his own work led to the exact formula. The Bekenstein-Hawking entropy states that the entropy of a black hole is exactly proportional to the area of its event horizon, not to the volume of the space inside. This is a revolutionary equation. It directly links the thermodynamic concept of disorder, a quantum informational property, to pure geometry. It says the information content of this most mysterious object in the universe is not about how much stuff you can cram into it, but about the size of its surface. This is the smoking gun for pixelation. In everyday thermodynamics, the entropy of a gas arises because it is made of a vast number of discrete molecules. You cannot have half a molecule, so the entropy counts the number of fundamental, indivisible units and the ways they can be arranged. The Bekenstein-Hawking formula does the same thing for spacetime itself. By giving us an exact number for the entropy of a horizon, it implies that the surface is not perfectly smooth. It must be woven from a finite number of incredibly tiny, fundamental patches, each carrying a single bit of quantum information. The smooth, curved geometry of the horizon we calculate with Einstein's equations is not the fundamental truth. It is a statistical average, an emergent picture that arises from the collective behavior of trillions upon trillions of these spacetime pixels. Just as a digital photograph looks smooth from a distance but reveals its blocky pixels when you zoom in, the fabric of spacetime may have a fundamental graininess, a minimal possible size, revealed only when we ask how much information it can ultimately hold. This formula transforms the event horizon from a mere boundary into a cosmic ledger, and its entries are the discrete quantum threads from which reality is sewn. The Bekenstein-Hawking entropy gave us a number, but Hawking's own later discovery gave that number a voice. Hawking radiation is the faint thermal glow that every black hole is predicted to emit. Its origin is a masterpiece of quantum weirdness, and it serves as our sixth clue. According to quantum theory, the vacuum of space is not empty. It is a turbulent sea of virtual particle pairs constantly flickering into existence and then annihilating each other almost instantly. This happens everywhere, even right in front of you. Normally, these pairs vanish without a trace, borrowing energy from the vacuum and repaying it in an instant. But at the very edge of a black hole's event horizon, the gravitational grip is so severe it can tear these pairs apart. Imagine one of these virtual particles appearing just outside the horizon. In a violent gravitational tug-of-war, one particle gets pulled across the point of no return into the black hole, while its partner is flung outward into space, free from annihilation. To an outside observer, this escaping particle looks exactly like thermal radiation, a slow, steady heat emanating from the black hole itself. This is Hawking radiation. The critical point is its temperature. Hawking calculated that this radiation has a precise thermal spectrum, meaning it carries a specific temperature that depends only on the black hole's mass. A smaller black hole would be hotter, radiating more fiercely. This thermal nature is the key clue. In our everyday world, thermal radiation, like the glow from a hot stove, is never fundamental. It is an emergent property. The heat and light come from the collective, statistical jostling of countless atoms and molecules. The smooth spectrum of warmth emerges from their chaotic dance. Hawking radiation behaves in exactly the same way. Its perfect thermal signature suggests it is not coming from some fundamental particle or field within the black hole. Instead, it is emerging from the chaotic, statistical behavior of the underlying quantum structure of spacetime at the horizon. The event horizon acts like a scrambler, taking any information that falls in and churning it into this featureless thermal noise. The precise mathematical form of this radiation, its spectrum, is potentially a direct window into that hidden quantum architecture. Just as the specific frequencies of light emitted by a hot gas reveal the identity of its atoms, the detailed properties of Hawking radiation could, in principle, reveal the fundamental units, the pixels of spacetime itself. It is as if the black hole is whispering to us in a code of heat, and that code describes the very grain of reality from which the horizon is woven. If we could ever detect and decode this whisper, we might read the blueprint for emergence. But this radiation creates a new tension, for as the black hole glows, it slowly loses mass and evaporates. What happens to all the information it swallowed when the black hole itself finally vanishes? Hawking radiation whispers of a hidden structure, but its implications lead to an even deeper mystery woven into the fabric of empty space itself. This brings us to the seventh clue, a problem so severe it is often called the worst prediction in the history of physics. It is the staggering puzzle of vacuum energy, also known as the cosmological constant. According to our best quantum theories, empty space is not nothing. It is a vibrant, seething foam of virtual particles constantly flickering in and out of existence. Every single point in this quantum vacuum is believed to possess a tiny, intrinsic energy. When physicists try to calculate how much energy this adds up to across the entire universe, they perform a straightforward sum. They add up the contributions from every possible quantum field, from every possible vibration. The result is not just large, it is catastrophically, unimaginably enormous. The calculated energy density of the vacuum should be around 1 followed by 120 zeros greater than what we actually observe. If this prediction were correct, the universe would have torn itself apart in a violent expansion moments after the Big Bang. Stars, planets, and life would be impossible. Yet our telescopes show a cosmos that is, by comparison, incredibly serene and gently expanding. The vacuum energy we actually measure is almost zero, but not quite. We know it exists because it is the driving force behind the accelerating expansion of the universe, a kind of anti-gravity woven into space itself. The discrepancy between prediction and reality is the largest gap ever seen in science. It is not a small error. It is a scream from our equations that something is profoundly wrong with our picture of spacetime at its most fundamental level. This is not a minor puzzle to be tweaked. It is a glaring sign that treating empty space as a simple backdrop where quantum fields live is a fatal mistake. The vacuum energy catastrophe suggests that spacetime itself must have a different origin, one where the naive idea of summing up infinite quantum jitters simply does not apply. In an emergent framework, the energy of the vacuum would not be a property of empty space because empty space as a fundamental entity would not exist. Instead, what we perceive as the quiet, energetic vacuum would be a collective state, a statistical average of an underlying quantum system, much like the calm surface of a lake emerges from the frantic motion of countless water molecules. In such a system, the cosmological constant would not be calculated by an infinite sum, but would be determined by the overall architecture and dynamics of the network from which spacetime emerges. The fact that our universe has a tiny, positive vacuum energy could then be a clue about the specific way that network is configured, a signature of its quantum code. The vacuum energy problem is not just an embarrassment, it is a cosmic signpost. It points away from spacetime as a fundamental stage and towards something more complex, more relational, and deeply hidden from our classical view. The quiet of empty space is not the same for everyone. An astronaut floating freely in the void perceives a cold, dark vacuum, utterly still. But if that same astronaut were to fire their rockets and accelerate at a constant rate, their experience of reality would transform dramatically. Their instruments would suddenly detect a warm bath of particles surrounding them, a gentle heat permeating what was just moments ago a perfect nothingness. This is not a malfunction, it is the Unruh Effect, our eighth profound clue. It reveals that particles and even temperature are not absolute properties of spacetime itself. They are relational phenomena entirely dependent on the observer's own state of motion. For the accelerating astronaut, the quantum fields that fill the universe appear excited, manifesting as real, detectable particles with a specific temperature. For the inertial, coasting observer, those same fields remain in their quietest state, and the particles simply do not exist. This is a staggering blow to our classical intuition. It tells us that what we call a particle, a fundamental building block of matter, is not a little ball that exists independently in space. It is more like a note in a symphony, a particular excitation of an underlying quantum field that only becomes audible, only becomes real under certain conditions of motion. The vacuum itself is not an empty stage, it is a quantum field in its ground state, and acceleration through it is like dragging a stick through calm water, creating ripples and waves that were not there before. The Unruh Effect demonstrates that reality is deeply participatory. The observer is not a passive spectator on a pre-built stage. They are an active participant whose own motion helps determine which aspects of the quantum field become real for them. This relational quality is a powerful hint at emergence. In a truly fundamental, absolute spacetime, one would expect concepts like particles and temperature to be intrinsic features. But if spacetime is an emergent phenomenon born from a more basic quantum network, then its properties would naturally be relational, dependent on how one interacts with that network. The warmth felt by the accelerating observer is not coming from nowhere. It is emerging from their specific journey through the hidden quantum structure of what we call the vacuum. It is as if the smooth, continuous stage of spacetime is a simplified interface. An acceleration is a command that reveals the raw, statistical data churning beneath it. The Unruh Effect whispers that our most basic experiences of reality, of things being here or there, hot or cold, are not fundamental truths, but stories told by our particular path through a deeper, more mysterious quantum world. The warmth of the Unruh Effect is a powerful illusion of motion, but an even deeper illusion may be woven into the very fabric of our existence. When physicists attempt to merge general relativity with quantum mechanics into a single, unified theory of quantum gravity, they encounter a conceptual abyss. In their most fundamental equations, like the famous Wheeler-DeWitt equation, something vital goes missing. Time simply vanishes from the mathematics. The equations describe a universe that is, at its core, static and frozen. This is the profound problem of time, our ninth cosmic clue. The equations of quantum gravity do not tell a story of change and becoming. They present a single, timeless snapshot of the entire cosmos, all at once. It is as if the universe is not a movie playing frame by frame, but a single, vast photograph containing every moment simultaneously. This seems to contradict everything we experience. Our lives are a relentless flow from past to future, a sequence of cause and effect. How can the fundamental theory of reality have no place for time itself? This glaring omission is not a mistake in the math. It is a feature, a screaming hint. Many researchers now believe it means that time, as we perceive it, is not a fundamental ingredient of the universe. It is an emergent property, a collective illusion that arises only under certain conditions. Think of it like the concept of temperature. A single molecule does not have a temperature. Temperature is a statistical property that emerges when you have a vast collection of molecules jostling chaotically. In a similar way, the flow of time may emerge from the statistical behavior of the underlying quantum network from which spacetime is woven. Our experience of a moment called now and a direction called forward could be a thermodynamic phenomenon, much like the arrow of time that emerges from increasing disorder. We perceive time because we, as complex systems made of countless particles, are embedded within this emergent structure and can only process information in one statistical direction. The timeless equations of quantum gravity describe the fundamental quantum reality, the complete picture. Our flowing time is what we see when we look at that picture from within it, when we are limited and cannot see the whole. The problem of time is not a problem to be solved by putting time back into the equations. It is a clue that we must learn to see the universe without it, to understand that the relentless tick of the clock is the sound of a grand and beautiful approximation. The timeless equations suggest a frozen cosmos, but our experience screams of motion and change. This paradox forces us to consider a radical new architecture for reality itself, one where the very points of spacetime are not smooth, but countable and discrete. This is causal set theory, our 10th compelling clue. Imagine trying to build the smooth curve of a shoreline using only individual grains of sand. From a distance, the shoreline appears continuous, but up close, you see its fundamental graininess. Causal set theory proposes that spacetime is like that shoreline, constructed from a vast collection of discrete, indivisible points. But these are not points in a pre-existing space. Instead, each point represents a fundamental event, and the entire structure of reality is defined purely by the causal relationships between them. Which event can influence which other event? This web of cause and effect, this pure ordering of happenings, is the primary reality. From this sparse, minimalist network of causal links, the familiar four-dimensional geometry of space and time is meant to emerge, like a three-dimensional image emerging from a carefully arranged set of dots. The theory is breathtaking in its simplicity. It does not assume space or time to begin with. It builds them from the ground up using only the logic of cause and consequence. But if this is true, if spacetime has a fundamental graininess, then it must leave a fingerprint on the universe we can observe. The granularity would impose a limit on how precisely events can be located, a kind of quantum fuzziness at the tiniest scales. This could have a direct, testable consequence for some of the most energetic messengers in the cosmos. Photons of extremely high energy, like those from distant gamma-ray bursts, travel across billions of light-years to reach us. According to our smooth spacetime theories, all photons from the same burst, regardless of their energy, should arrive at exactly the same time. But if spacetime is a causal set, a discrete lattice, then the highest energy photons might interact with this granular structure in a subtle way. Think of it like light passing through a fine mist. The mist is made of tiny droplets, and while most light passes through, the very highest energy light might scatter in a minuscule, cumulative way. For photons on a billion light-year journey, this could mean that the highest energy ones lag ever so slightly behind their lower energy siblings. This energy-dependent delay would be a smoking gun, a direct signal from the pixelated fabric of reality itself. While such an effect has not been conclusively seen yet, the very possibility transforms causal set theory from a philosophical idea into a framework with concrete, observational stakes. It offers a promise that the deepest structure of reality might one day be revealed not just in the mathematics of black holes, but in the faint, time-stamped signatures of ancient cosmic explosions. Causal sets offer one path from discrete points to smooth geometry, but another theory provides a breathtakingly detailed blueprint. Loop quantum gravity takes the idea of pixelated space and gives it a vibrant, quantum mechanical life. In this framework, space itself is not continuous. It is woven from tiny, indivisible loops of gravitational field, threads of pure geometry. The theory's central objects are called spin networks. Picture a vast, ever-changing cosmic web, a network of lines connecting at nodes. Each line carries a quantum number, a spin, that represents a specific, discrete unit of area. Each node where lines meet represents a discrete unit of volume. This is not a graph drawn on a pre-existing space. This network is space. The entire three-dimensional geometry of the universe at a given instant is described by a single, colossal spin network. Distances, angles, and volumes are not measured with rulers, but are calculated from the quantum numbers and connections of this fundamental graph. What we perceive as empty space is simply a region of the network where the quantum numbers are at their lowest possible values, a quiet, minimal hum of geometry. Matter and energy are not separate things placed into this space. They are excitations of the network itself, like particular patterns of vibration traveling along its threads. The smooth, continuous spacetime of Einstein's equations does not exist at this fundamental level. It is an illusion that emerges in the same way the smooth flow of a liquid emerges from the chaotic dance of countless molecules. When we zoom out from the frenetic quantum jitter of the spin network, when we average over a vast number of these discrete quanta of area and volume, the classical, smooth geometry of general relativity is predicted to coalesce. This is the high-density limit, not of matter but of information, where the quantum graininess becomes too fine for our classical instruments to detect. The promise of loop quantum gravity is not just philosophical, it is potentially testable. Because it rewrites the rules of geometry at the smallest scales, it changes the story of the universe's very beginning. In the standard Big Bang model, we trace cosmic history back to a singularity, a point of infinite density where the laws of physics break down. In loop quantum gravity, the quantum nature of space prevents this collapse. The spin network cannot be squeezed to zero size. Instead, as we rewind time, we reach a moment of maximum compression and then a quantum rebound. This leads to cosmological models predicting a big bounce, a universe that existed before our own, contracted to a hot, dense state, and then expanded again into the cosmos we see today. Such a model could leave subtle imprints on the oldest light in the universe, the cosmic microwave background, a faint pattern that future telescopes might one day read. The spin network is a vision of reality where space is not a container, but a dynamic quantum tapestry, and its threads may hold the secret to what came before our own beginning. The spin network offers a quantum vision of space, but our telescopes reveal a cosmos behaving in a way that defies all classical expectation. At the largest scales, the universe is not just expanding, it is accelerating. Distant galaxies are rushing away from us faster and faster as time goes on, as if an invisible force is pushing space itself apart. This discovery, known as late-time cosmic acceleration, is our 12th profound clue. To explain it, cosmologists invoked a mysterious component called dark energy, a kind of anti-gravity woven into the fabric of the vacuum, but its nature is utterly unknown. In the standard model, dark energy is treated as a new, fundamental field with a constant energy density, the cosmological constant. Yet, as we saw earlier, the quantum calculation of this vacuum energy is catastrophically wrong. This mismatch suggests a radical alternative. Perhaps dark energy is not a new ingredient at all. What if it is a collective effect, a low-energy echo of the underlying quantum structure from which spacetime emerges? Think of a calm lake on a windless day. Its smooth, flat surface is an emergent property of countless water molecules. Now, if you were to observe the lake very subtly expanding, the water level rising imperceptibly, you would not need to invent a new type of water to explain it. You would look for a change in the collective state of the system, perhaps a shift in temperature or pressure affecting the entire body. In a similar way, dark energy could be a thermodynamic signal from the hidden quantum network. As the universe expands and cools, the quantum degrees of freedom that weave spacetime together may enter a new phase, a state where their collective interactions naturally produce a gentle, repulsive effect on cosmic scales. This would mean that the force driving galaxies apart is not a ghostly field filling space, but a property of space itself, or rather, of what space fundamentally is. The acceleration would be an emergent phenomenon, a direct consequence of the architecture and evolution of the quantum reality underpinning our cosmos. In this view, the puzzle of dark energy transforms. It is no longer a search for a missing particle, but a search for the correct theory of how spacetime emerges from something deeper. The faint push accelerating the universe could be the most visible signature of that deeper structure, a cosmic clue written in the motion of galaxies, pointing back to the quantum threads from which everything is woven. The accelerating expansion of the cosmos hints at a deeper structure, but to uncover it we must ask how a pixelated reality could ever appear so smooth. If spacetime emerges from a quantum network, that network must be incredibly fine-grained, its fundamental units far smaller than anything we can currently probe. But there is a critical test for any such theory. Our universe, as described by Einstein's special relativity, possesses a profound symmetry called Lorentz invariance. This principle states that the laws of physics are the same for all observers moving at constant velocity. There is no preferred state of rest, no hidden grid against which the universe is measured. A spaceship coasting at half the speed of light and a laboratory on Earth both conduct identical experiments and get identical results. This symmetry is woven into the very mathematics of our most successful theories. For an emergent spacetime model to be viable, it must reproduce this perfect symmetry at the energies and scales we experience. The underlying quantum network cannot have a built-in favorite direction or a secret ticking clock that breaks the rules. It would be like building a perfectly round wheel out of tiny, square blocks. From a distance, the wheel looks perfectly smooth and symmetrical, even though up close you can see the jagged bricks. The challenge for any theory of quantum gravity is to ensure that its fundamental, jagged building blocks average out to produce the perfectly smooth, symmetrical wheel of Lorentz invariance that we observe. This is a severe constraint. If the network had a preferred frame, a kind of quantum ether, it would leave subtle fingerprints. For instance, the speed of light might vary imperceptibly depending on the direction the photon traveled relative to this hidden grid, or on the photon's own energy. Physicists have devised exquisitely precise experiments to hunt for these fingerprints. They study the light from distant gamma-ray bursts, comparing the arrival times of high-energy and low-energy photons that have traveled for billions of years. Even a minuscule difference, a lag of a fraction of a second over that immense journey, would signal a crack in Lorentz invariance, a whisper of the underlying granular structure. So far, no such crack has been found. The universe, to the limits of our ability to measure, appears perfectly smooth and symmetrical. This null result is itself a powerful clue. It tells theorists that whatever the fundamental quantum reality is, it must be chaotic and rich enough that its statistical average completely washes out any sense of a preferred direction or frame. The emergence must be so efficient that the classical illusion of a seamless, symmetric stage is flawless. This pushes the scale of the fundamental grains far below our current reach, but it also guides the search, telling us that the true theory must hide its quantum skeleton with breathtaking perfection. The flawless symmetry we observe is a monumental achievement for any theory of emergence, but a true theory must do more than hide its seams. It must also account for the numbers, the precise quantities we measure in the cosmos. This brings us to a landmark calculation, a moment where abstract theory touched the hard reality of a black hole's entropy. In the late 1990s, a breakthrough occurred within string theory that sent shockwaves through the world of theoretical physics. Researchers managed to do something many thought impossible. They counted the quantum microstates of a specific type of black hole. Their method was to use string theory's core idea that the fundamental entities are not point particles but tiny, vibrating strings. By carefully constructing a black hole from a precise configuration of strings and branes, multidimensional objects within the theory, they could analyze its quantum description. They then asked a straightforward but profound question: how many distinct quantum configurations, how many unique vibrational patterns of these strings and branes could possibly produce a black hole with the exact same mass and charge? They painstakingly enumerated every possible arrangement, every microscopic way the system could be built while looking identical from the outside. The result was breathtaking. The number of these microstates was astronomically vast but not infinite. When they calculated the entropy implied by this count, using the classic formula from statistical mechanics, it matched the Bekenstein-Hawking entropy perfectly. The area of the horizon, expressed in Planck units, was not just proportional to the entropy, it was the entropy. This was not an approximation or a suggestive hint. It was an exact first principles derivation of the most important number in black hole thermodynamics from a counting of underlying quantum degrees of freedom. This success is a colossal clue. It demonstrates concretely that the smooth, classical horizon is a facade. Its area is a direct measure of the logarithm of the number of hidden quantum configurations lurking behind it. The black hole is not a simple object with a mysterious temperature. It is an unfathomably complex system in a maximum entropy state, and its surface area is the screen upon which that complexity is projected. This microstate counting is a direct validation of the core emergent spacetime idea. It shows that spacetime geometry, in this extreme limit, is not the primary reality. It is a thermodynamic collective description of a deeper, bustling quantum system. The horizon is not a place where space ends, but where our classical understanding dissolves into a sea of quantum possibilities, each one a different thread in the tapestry of reality. The microstate counting proved a horizon's secrets are quantum, but what if those secrets are the very glue of reality? This leads us to the 15th clue, a conjecture so elegant it feels like a key turning in a cosmic lock. It is called ER equals EPR. The equation is simple, but its meaning is universe-shattering. On the left, ER stands for an Einstein-Rosen bridge, better known as a wormhole, a hypothetical tunnel through spacetime connecting two distant points. On the right, EPR stands for Einstein-Podolsky-Rosen entanglement, the spooky quantum connection where two particles, no matter how far apart, share a single quantum state. The conjecture boldly states they are the same thing. Quantum entanglement is not just a correlation described by mathematics. It is physically built from microscopic spacetime plumbing. Every entangled pair of particles is invisibly linked by a tiny quantum wormhole. This idea directly geometrizes quantum information, turning an abstract link into a literal stitch in the fabric of reality. Think of it like this. Imagine two friends holding the ends of a very long, invisible rope. They can feel each other's tugs, but the rope itself is hidden. In the old quantum view, entanglement was like that invisible connection, a mathematical link with no physical medium. The ER equals EPR conjecture says the rope is real. It is a thread of spacetime itself, a tunnel so unimaginably tiny and transient it defies our classical picture, but it is there, weaving the particles together. This transforms our understanding of what space is. If every quantum entanglement is underwritten by a microscopic wormhole, then the connectivity of space, the very fact that 2 points can influence each other, is built from a dense web of these threads. The smooth, continuous geometry we perceive is not a stage on which entanglement happens. It is the emergent, large-scale picture of countless quantum threads intertwining. Where entanglement is dense, space is strongly connected, objects are close. Where there is no entanglement, there is no space, no connection at all. The fabric of the cosmos is quite literally a fabric, woven from the quantum links between things. This means spacetime does not create entanglement. Entanglement creates spacetime. The wormholes are the fundamental stitches, and the smooth cloth of the universe is what we see when we stop looking at the individual threads. If entanglement weaves the fabric of space, then the very idea of things happening in specific places may be the grandest illusion of all. This brings us to a 16th clue, a discovery so elegant it seems to rewrite the rules of reality from a place beyond space and time. In the world of particle physics, scientists spend immense effort calculating what happens when particles like electrons or photons collide and scatter. These probabilities, called scattering amplitudes, are the foundation for predicting everything from the outcome of experiments in giant colliders to the nuclear reactions that power stars. For decades, the method for calculating these amplitudes was tortuously complex, involving thousands of Feynman diagrams that tracked every possible path and interaction through spacetime. The process assumed locality, the principle that particles interact at definite points in space and time. Yet, in 2013, researchers made a stunning breakthrough. They found that the results of these fantastically complicated calculations could be derived from the geometry of a single, beautiful, multi-dimensional shape they called the Amplituhedron. The mathematics was breathtakingly simple and direct. More astonishing was what the calculation left out. It made no reference whatsoever to spacetime. It did not use the concepts of locality or unitarity, which are the bedrock of our conventional quantum theories. The Amplituhedron geometry simply gave the right answer, as if it were accessing a deeper, more fundamental layer of reality where notions of here and there, before and after, are not yet defined. Think of it like listening to a symphony. The old method was like trying to understand the music by analyzing the vibration of every individual violin string and air molecule in the concert hall, a chaotic web of local interactions. The Amplituhedron approach is like being handed the pure mathematical score of the symphony itself, a complete description of the beauty that emerges without any reference to the specific instruments or the hall it will be played in. This geometric object exists in a realm of pure information and relationship. The fact that it perfectly describes particle collisions suggests that spacetime and locality are not the stage upon which the quantum world plays out. They are the symphony we perceive, a rich, emergent consequence that arises only when we translate that deeper, spaceless geometry into the language of our experience. The Amplituhedron whispers that the universe at its heart may be a shape, and our reality of separate events unfolding in a vast container is just one way of hearing its music. The geometry of the Amplituhedron exists in a spaceless realm, but our own universe had a definite beginning in an event of unimaginable energy. To understand that origin, cosmologists rely on the story of inflation, a period of hyper-fast expansion in the universe's first fleeting moments. This theory elegantly explains the large-scale structure we see today, the vast web of galaxies and cosmic voids. It proposes that microscopic quantum fluctuations, tiny ripples in the fabric of reality, were stretched to astronomical sizes by this explosive growth, eventually seeding the formation of everything we see. Yet this beautiful story contains a hidden flaw, a paradox that cuts to the heart of our classical understanding. This is the Trans-Planckian Problem, our 17th cosmic clue. To see the issue, we must rewind the cosmic film. We observe a galaxy cluster today, trace its origin back to a quantum fluctuation during inflation. As we rewind, the wavelength of that fluctuation shrinks. By the time we reach the very beginning of inflation, just a tiny fraction of a second after the universe's birth, the mathematics tells us that the wavelength of this seed becomes smaller than the Planck length. This is the fundamental scale in physics, about 1.6 times 10 to the negative 35th meters, a distance so inconceivably tiny it is believed to be the scale where the smooth, classical picture of spacetime must shatter into quantum foam. The problem is stark. Our theory of inflation uses Einstein's equations, which treat spacetime as a smooth, continuous stage, to describe the stretching of these fluctuations. But it is using this classical stage to describe a process that, according to its own timeline, originated in a domain where the stage itself does not exist. It is like using the rules of fluid dynamics, which describe the smooth flow of water, to track the path of a single molecule back to a time when the water was not even a liquid, but a disorganized cloud of individual atoms. The theory is trying to speak a language of continuity about an event that was fundamentally discrete. This is not a minor technicality. It suggests that our entire narrative of the universe's origin, as compelling as it is, may be built on a conceptual sandcastle. The Trans-Planckian Problem forces us to confront a profound possibility. To truly understand cosmic genesis, we cannot simply apply quantum mechanics to a classical spacetime background. We need a framework where spacetime itself is quantum, where it emerges from something more basic. We need a theory where the question of what existed before inflation, or what existed at those unimaginable densities, is not a question about things in space and time, but about the quantum genesis of space and time themselves. The seeds of our entire cosmic structure may have been sown in a realm where here and there had no meaning, a realm whose quantum code we are only beginning to decipher. The Trans-Planckian Problem reveals a crack in our classical story of creation, but some theories are designed to build the universe from the ground up, one quantum step at a time. One such approach, causal dynamical triangulations, offers a radically different vision. It does not assume a smooth, four-dimensional continuum exists from the start. Instead, it imagines constructing spacetime from its most basic possible ingredients. Picture a colossal box of geometric Lego blocks, but these are not ordinary bricks. Each block is a tiny, four-dimensional shape, a simplex, representing the smallest possible chunk of spacetime with a built-in arrow of time, a causal structure. The theory's goal is to discover what kind of large-scale universe naturally emerges from the quantum jumble of these blocks. To do this, it employs a technique from quantum physics called the path integral. The idea is to consider every single possible way these tiny blocks could be glued together, every conceivable microscopic spacetime configuration, no matter how wild and crumpled. Each configuration gets a quantum probability weight. The true physical universe that we experience is not one specific arrangement, but the quantum sum, the superposition of all these possible arrangements, with the most probable ones dominating. It is like asking what shape a pile of sand will take. You do not just look at one grain, you consider the statistical behavior of trillions of grains, and a smooth dune emerges. When researchers perform this gargantuan summation on supercomputers, something remarkable happens. A stable, classical universe bubbles out of the quantum chaos. But it comes with a breathtaking prediction. The effective dimensionality of this emergent spacetime is not fixed. It depends entirely on the scale at which you probe it. At the large scales of our everyday world and of cosmology, the triangulations average out to produce a perfectly smooth, four-dimensional continuum, exactly as Einstein described. But if you could theoretically zoom in, down toward the Planck scale, the fabric of reality behaves in a profoundly different way. The calculations show that the effective dimension begins to shrink. It smoothly runs from 4 down to 2. At the very smallest scales, spacetime appears to become two-dimensional. This running dimension is a direct mathematical signature of emergence. It tells us that dimensionality itself is not a fundamental property of the universe's bedrock. It is an emergent quality that changes depending on how closely you look. Think of the surface of a ball of steel wool. From a distance, it looks like a solid, three-dimensional ball. As you move closer, you see it is made of a tangled, three-dimensional mesh of wires. Get even closer, and at the scale of a single wire, the structure effectively becomes one-dimensional, a line. The dimension you measure depends on your resolution. In causal dynamical triangulations, the universe itself undergoes this transformation. The four-dimensional expanse we call home is the large-scale statistical reality. Its two-dimensional ghost at the Planck scale is a glimpse of the sparse causal network from which it is woven, a network where the familiar concepts of volume and distance have not yet coalesced. This running dimension is more than a curious prediction. It is a potential target for future physics. If effects from this microscopic two-dimensional regime somehow imprint on the oldest light in the cosmos or on the behavior of ultra-high energy particles, we might one day detect the shadow of the universe's true skeletal form. This radical reimagining of wormholes as the fabric of entanglement leads to an even more astonishing possibility for the darkest places in the cosmos. If spacetime is woven from quantum links, then what exactly is on the other side of a black hole's event horizon? The classical answer is a region of space leading to a singularity. But a new, breathtaking proposal suggests the interior is not a place at all, at least not in any conventional sense. Instead, it is a ghostly reality conjured into being by entanglement itself. The idea begins with the puzzle of information. We know from the holographic principle that all the data about what fell into the black hole is smeared across its two-dimensional surface. But our intuition screams that there must be something inside, a continuation of space. This new view reconciles these facts in a stunning way. It proposes that the interior of the black hole is not a separate, pre-existing region that you enter. It is a computational reality, a dynamic simulation that is generated in real time by the complex quantum entanglement between two very different things. The first is the Hawking radiation that has already escaped into the universe, carrying away tiny bits of the black hole's information. The second is the remaining mass of the black hole itself, and the quantum degrees of freedom still associated with its horizon. Their intricate, evolving entanglement does not just describe the interior, it actively constructs it. Think of it like a massively multiplayer online game. The players, represented by the Hawking radiation quanta and the horizon's quantum data, are all following a shared set of rules and constantly exchanging information. None of them are inside a castle on the game's map, but through their interactions and shared state, the castle, its halls, its treasures, its very geometry emerges as a consistent reality for all of them. In this view, an astronaut falling into the black hole is not traveling to a pre-made location. They are becoming a new player in this quantum game, and their experience of crossing the horizon and moving inward is the process of their own quantum information becoming entangled with this vast system, thereby participating in the real-time rendering of the interior geometry. This means the smooth spacetime inside the black hole is a collective hallucination, a story told by the quantum correlations between the outside and the remains of the whole. It is a region that exists only as long as the entanglement that builds it persists. As the black hole evaporates away to nearly nothing, that entanglement is transferred, and the interior simply winks out of existence, not with a collapse but like a dream fading upon waking. This transforms the black hole from a cosmic pit into a dynamic processor, where space-time is not the stage for quantum events, but the final, fleeting output of the most intense computation in the universe. The black hole's interior may be a quantum hallucination, but there is another horizon far more vast and inescapable, one that surrounds us all. As our universe accelerates, driven by dark energy, it creates a boundary at the farthest edge of our possible perception. This is the cosmological horizon, the ultimate limit to how far we can ever see, because beyond it, galaxies are receding faster than the speed of light, their light never able to reach us. This is not a physical barrier like the edge of a black hole, but a causal one, a permanent curtain drawn by the expansion of space itself. And here lies our 20th clue, a stunning parallel that ties the entire cosmos into the emergent story. This cosmological horizon, like the event horizon of a black hole, also has a temperature and an entropy. This is known as de Sitter entropy, named for the spacetime that describes an accelerating universe. The mathematics is clear and profound. The entropy of our cosmic horizon is once again proportional to its area. this is not a metaphor or a vague suggestion. It is a concrete, calculable property of the vacuum we inhabit. The entire observable universe, everything we could ever hope to see or interact with, is bounded by a surface that holds a specific, finite amount of information, just like a black hole. This realization is a thunderous echo. It tells us that the principle of holography is not confined to the violent extremes of collapsed stars. It is a universal feature of any causal boundary in a universe governed by quantum gravity and acceleration. If a black hole's horizon is a screen encoding the interior, then our cosmic horizon is the ultimate screen, potentially encoding everything within our observable universe. The space we experience, with its hundreds of billions of galaxies, may be a grand projection from the quantum data living on this distant, spherical boundary at the end of time. This transforms our place in the cosmos. We are not just living in the universe, we may be living inside it, with the entire story of our reality written on its inner skin. The fact that this gentle, expansive horizon carries entropy means it, too, must have fundamental degrees of freedom, pixels of reality. The quiet, accelerating vacuum is not empty. It is in a maximum entropy state, a state of equilibrium, which is why it appears so uniform and featureless to us. The de Sitter entropy is a number that measures the staggering number of microscopic quantum configurations that all yield the same smooth, accelerating cosmos we see. It is the signature of the universe's underlying quantum structure, written not in the fiery heart of a singularity, but in the cold, vast stillness of our expanding future. This horizon is not a place we will ever reach, but its existence as an entropy-bearing surface is a quiet, omnipresent clue that emergence is not a special effect for black holes. It is the operating system of reality itself. The perfect symmetry of Lorentz invariance is a testament to how flawlessly the classical world emerges from the quantum realm. Yet, to truly prove that spacetime is woven from discrete threads, we would need to catch it in the act, to find a place where that smooth facade shows a single, telltale crack. This search for a fundamental graininess brings us to our 21st clue, a hunt for the most subtle of cosmic speed traps. If spacetime has a pixelated structure, a kind of invisible quantum grid, then the very speed of light might not be a perfect constant. In a perfectly smooth, continuous universe, a photon of any energy, from the faintest radio wave to the most powerful gamma ray, must travel at exactly the same speed across the vacuum of space. This is a cornerstone of Einstein's relativity, but if space is fundamentally grainy, like a digital image, then the highest energy photons, with their incredibly short wavelengths, might interact with that granularity in a minuscule way. Think of it like running across two different surfaces. A sprinter on a perfectly smooth track and on a slightly pebbled one will, in theory, post the same time. But if you could measure with infinite precision, you might find that on the pebbled surface, their foot strikes cause imperceptible slips and adjustments, slowing them by a fraction of a second. For a gamma-ray photon traveling across billions of light-years, a similar effect could accumulate. The photon's journey would not be through a perfectly smooth void, but through a quantum foam, and that might cause the highest energy light to lag ever so slightly behind its lower energy companions. This predicted effect is called vacuum dispersion, and its detection would be a revolutionary smoking gun. It would mean that the universe has a preferred frame, a hidden grid, and that the speed of light depends on energy, violating the sacred principle of Lorentz invariance. To hunt for this effect, astronomers turn to some of the most violent explosions in the cosmos, gamma-ray bursts. These events, often the death cries of massive stars collapsing into black holes, flood the universe with photons of wildly different energies, all launched at the same instant. By the time this light reaches our telescopes, it has traveled for eons across the cosmos. Scientists then perform an exquisitely precise analysis, comparing the arrival times of the highest energy gamma rays with the lower energy ones. A delay, even one measured in milliseconds over a journey of billions of years, would be a direct message from the fabric of reality, a signal that space-time has a grain. So far, after studying countless bursts, no such delay has been conclusively found. The light, to the limits of our phenomenal precision, arrives in perfect unison. This null result is itself profoundly informative. It tells us that if spacetime is emergent and discrete, the scale of its fundamental grains must be far, far smaller than our current observations can probe, or that the emergence is so efficient it completely hides any directional preference. The ongoing search continues, a silent testament to our desire to see behind the curtain. Every new gamma-ray burst is another chance that the universe might finally blink, revealing the pixelated truth beneath its seamless face. Gravity can leave a permanent scar on the fabric of space. When a powerful gravitational wave, a ripple in spacetime from a cataclysmic event like colliding black holes, washes over a region, it does more than just stretch and squeeze space temporarily. As it passes, it can actually induce a tiny, permanent displacement in objects floating freely in its path. Imagine a buoy resting on a calm ocean. A massive wave rolls through, lifting and dropping it. When the water settles, the buoy is not exactly where it started. It has been shifted ever so slightly by the wave's passage. This is the gravitational memory effect, a subtle but real fingerprint that extreme gravity can etch onto the geometry of the universe. For physicists, this is far more than a curious prediction. It is deeply intertwined with some of the most fundamental symmetries and conservation laws in nature, specifically linked to what are called soft particles or soft gravitons. These are hypothetical particles of incredibly low energy, essentially the gentlest possible whispers of gravity itself. Theoretical work suggests that the gravitational memory effect is the classical, observable imprint of these soft gravitons at work. The connection points to something profound about the infrared structure of quantum gravity, the physics of the very longest wavelengths and lowest energies. It hints that spacetime at its most fundamental level possesses a vast and rich symmetry, a kind of infinite-dimensional soft hair that governs how it responds to and remembers every gravitational event. In an emergent spacetime framework, this is a potential goldmine. The symmetries revealed by the memory effect and soft gravitons could be direct clues about the architecture of the underlying quantum system from which spacetime emerges. They are like the hidden rules of the quantum network, rules that mandate how it must behave and what it must remember when energy and information flow through it. This transforms the memory effect from a minor gravitational footnote into a potential observational bridge. Future ultra-sensitive detectors, like next-generation gravitational wave observatories, might one day measure these permanent displacements in the wake of colossal cosmic collisions. If they can, and if the data aligns with the predictions from soft particle theories, it would not just confirm another weird facet of gravity. It would provide a tangible, measured link between the smooth geometry of general relativity and the deep, symmetric quantum structure that may be its true origin. We would be reading the permanent record gravity writes upon reality, a record that may spell out the rules of emergence itself. But the search for a consistent quantum theory of gravity is not just a quest for what works, it is also a process of elimination, a way to map the boundaries of possible realities. This brings us to a fascinating and powerful concept in string theory known as the swampland. Imagine the landscape of all conceivable theories of physics. String theory suggests that within this vast landscape, there exists an island, a set of theories that can be consistently unified with quantum gravity. These are the self-consistent descriptions of reality that do not lead to logical paradoxes or mathematical impossibilities when gravity is included. The rest of the landscape, the infinite expanse beyond this island, is called the swampland. It is filled with theories that look perfectly sensible on their own, effective field theories that describe particles and forces beautifully, but which contain a fatal flaw. They cannot be coupled to quantum gravity without breaking down. They are, in essence, mathematical mirages, ideas that seem plausible but are fundamentally incompatible with the deeper architecture of a quantum universe. The Swampland program is the effort to chart this territory, to write the rules that distinguish the island from the swamp. And these rules, these Swampland conjectures, are not arbitrary. They emerge from the stringent mathematical consistency requirements of string theory itself. One of the most discussed conjectures deals directly with the mystery of dark energy. It proposes that the vacuum energy, the cosmological constant, cannot be a fixed, arbitrarily small positive number like the one we seem to observe. Instead, it must either be exactly zero or it must be large enough to be dynamically significant. A very tiny, stable positive value, according to this conjecture, sits squarely in the swampland. It describes a universe that string theory suggests is mathematically impossible to construct from its fundamental ingredients. This creates a tremendous tension with our observations of an accelerating universe driven by what appears to be a very small cosmological constant. The conjecture forces a dramatic re-evaluation. Either our measurement of dark energy is incomplete and it will turn out to be exactly zero or much larger, or dark energy is not a constant at all, but a dynamic field that is slowly evolving, a possibility that would place it back on the island of consistent theories. For the idea of emergent spacetime, the swampland is a crucial filter. Any proposed model for how spacetime emerges from a quantum network must not only reproduce Einstein's equations and quantum mechanics, it must also satisfy these deep consistency conditions to avoid being banished to the swampland. The conjectures act as a cosmic quality control, weeding out attractive but ultimately impossible visions of reality. They tell us that the quantum system from which spacetime emerges cannot be just any system. It must have very specific properties, like the inability to support certain types of ultra-stable, low-energy states. In this way, the quiet acceleration of our universe becomes a strict teacher. It is not just a puzzle to be solved, but a boundary condition that shapes the search for the true, fundamental theory, guiding us toward the narrow path where a quantum universe can consistently give birth to the smooth, expanding stage we call home. The universe's hidden graininess must be so fine that even our most powerful eyes see only a perfect, smooth finish. For decades, physicists have tried to catch this quantum foam in action, to witness the Planck-scale jitter that would betray spacetime's emergent nature. Their method is beautifully direct. If the vacuum is truly a seething foam of microscopic wormholes and virtual black holes, as some models suggest, then light traveling across the cosmos should be affected. A perfectly smooth spacetime acts like a flawless lens, preserving the sharpness of a distant point of light. But a foamy spacetime would be like looking through a windowpane of old, wavy glass. It would subtly blur and distort the image. The longer the journey, the more this blurring would accumulate. So astronomers turned their telescopes to the most distant, luminous beacons they could find, quasars at the edge of the observable universe. These brilliant points of light have traveled for billions of years. If spacetime has a rough texture at the Planck scale, their light should arrive slightly scrambled, its point-like image smeared just a little. Researchers meticulously analyzed the sharpness of these quasar images, searching for the telltale blur. Another approach used the incredible precision of interferometry, where combining light from multiple telescopes creates an instrument with the resolution of one as wide as the distance between them. A quantum foam would introduce random phase shifts in the light waves, creating a characteristic noise or blurring in the interferometric signal. The results, however, have been consistently silent. No blurring has been found. The images remain pin-sharp, and the interferometers see no extra noise. Each new, more sensitive observation places a tighter constraint on how rough spacetime can possibly be. These stringent null results are not failures. They are powerful guides ruling out entire classes of models for quantum gravity that predicted a foaminess we could already see. They tell us that if spacetime is emergent and grainy, that grain must be unimaginably fine, or its effects must be cunningly hidden from our classical probes. The smoothness is not an approximation. It is a perfectly maintained illusion, enforced by the underlying quantum rules with such efficiency that even light on a 10-billion-year journey cannot stumble. This observational silence pushes the fundamental scale of reality even further from our grasp, but it also sharpens the search, telling theorists that the true texture of spacetime lies in shadows far deeper than we have yet learned to see. The silence from the cosmos pushes our search for emergence into a new and unexpected realm, one that exists not in distant galaxies but right here on Earth. Our final cosmic clue comes from the physics of everyday materials, from the collective dance of atoms in a carefully tuned fluid. This is the world of analog gravity, where scientists create laboratory models of black holes to watch spacetime physics play out in a tank of supercooled atoms. The principle is breathtakingly elegant. Imagine a fluid flowing faster and faster until, at a certain point, it moves quicker than the speed of sound waves within it. Anything like a ripple or a sound particle called a phonon that finds itself on the wrong side of that boundary cannot escape upstream. It is trapped by a sonic horizon, a dumb hole as physicists wryly call it, an acoustic analog to a black hole's event horizon. In this controlled setting, the flowing fluid does not contain a spacetime horizon, it creates one. The effective geometry that governs how sound propagates, its effective spacetime, emerges entirely from the collective, quantum behavior of millions of atoms moving in unison. This emergent geometry can be made to perfectly mimic the equations of general relativity, complete with its own version of Hawking radiation. Researchers have indeed detected a thermal glow of phonons emanating from these sonic horizons, a whisper of analog Hawking radiation born from the quantum fluctuations of the fluid itself. This is not a mere curiosity, it is a profound demonstration. It shows concretely in a tabletop experiment how a perfect Lorentz invariance and a smooth, curved geometry can arise from an underlying system that is fundamentally discrete, quantum, and has no innate concept of spacetime. The atoms in the fluid do not know about relativity. They follow their own, simpler quantum rules, yet when they act together, they generate a collective reality where an effective speed of light, the speed of sound, exists, and where horizons with thermodynamic properties naturally form. Analog gravity provides a tangible, working model for the grand cosmic emergence we have been exploring. It suggests that our universe's spacetime may be like the sonic geometry in that fluid, a magnificent and convincing emergent phenomenon, a story told by the quantum chorus of whatever fundamental reality truly sings beneath the silence. The journey through these cosmic clues reveals a pattern more compelling than any single discovery. From the preserved information on a black hole's surface to the thermal whisper of Hawking radiation, from the relational warmth felt by an accelerating observer to the timeless equations of quantum gravity, a common thread runs through them all. Each clue, in its own way, chips away at the classical stage of absolute space and time. Black hole thermodynamics tells us that geometry is a measure of information. Quantum entanglement suggests that connectivity weaves the fabric of distance itself. The failure of locality in paradoxes like the firewall and the vanishing of time from fundamental equations indicate that our most basic intuitions about here and now are approximations that break down under extreme scrutiny. These are not disconnected puzzles, they are different facets of the same profound realization. The smooth, continuous spacetime of Einstein, the dependable container of our daily lives, appears less like the foundation of reality and more like a statistical average. It is the calm, collective surface that emerges from the frantic, discrete quantum interactions happening at a level we cannot directly perceive. No single clue is a definitive proof, but their collective weight forms a powerful convergence. The mathematics of black holes, the principles of quantum information, and the paradoxes of locality all point in one direction. They suggest that spacetime is not a fundamental ingredient, but a magnificent and convincing emergent description, a story our universe tells about itself at the energy scales we inhabit. It is a story woven from countless quantum threads, a narrative of such seamless complexity that it feels utterly real, even as its deeper origins remain hidden in the code of a more basic reality. This realization transforms the quest of physics at its deepest level. For decades, the Holy Grail has been to quantize gravity, to take Einstein's smooth geometric stage and chop it into tiny, discrete packets that obey the rules of quantum mechanics. But if these clues are pointing the right way, that entire endeavor is starting from the wrong premise. The goal is not to quantize spacetime, because spacetime is not the fundamental thing to be quantized. Instead, the true task is to understand how spacetime, and the gravity that bends it, spontaneously arise from a more primitive reality of pure quantum information and entanglement. Gravity would not be a force to be added to the quantum world. It would be the thermodynamic signature of that world's hidden complexity. Geometry would not be the canvas on which the universe is painted. It would be the painting itself, emerging from countless quantum brushstrokes. This shifts the center of reality from a stage to a network, from a container to a consequence. The next generation of experiments now carries this profound weight. Advanced gravitational wave observatories will listen not just for collisions, but for the faint echoes of soft gravitons and the permanent memory they might leave behind. Space telescopes will scrutinize the ancient cosmic microwave background for any imprint of a bouncing, emergent beginning. On Earth, ever more sophisticated analog gravity experiments and quantum simulators will act as miniature universes, letting us watch geometry and horizons crystallize from controlled quantum chaos in real time. Each effort is a search for the signature of the code, a test to see if the universe truly is a story told by something deeper. To consider this possibility is to see the cosmos with new eyes. We are not living inside a pre-built arena. We are participants in an ongoing emergence where the very space between us and the flow of time we share are the most intimate parts of a grand and hidden narrative. The universe is not a container for our existence. It is the magnificent and evolving consequence of it.